Hello and welcome back to the channel. It's Mark from PowerSonic and Apprentice 121. I'm excited about this one because we're going to do some testing. We're going to look at test results both in a grid connected state and also in island mode and have a look at the difference in those values and speak about the validity of some of the test results as well, because industry has some guidance and views around that I want to share through the course of this video. We're going to be working on the polar EESS inverter combined with battery storage, obviously, if we're going to be doing some off-grid testing, using the TNS MFT Pro Plus. And we're focusing in on your loop impedance values, so ZS or ZE for want of a better explanation, in the here and now, both in that grid connected state and also in the island mode state. So let's get straight to it. Let's see what some of this testing looks like, some of the values that we record and the reasons that that might be the case. So we're going to take a look at doing some electrical testing, both in grid connected mode and also in island mode. And I'm going to use the TNS MFT Pro Plus on this polar EESS system to see what effects that might have. So the polar EESS has a EPS output. This is the 6 kilowatt inverter, and it has got a 6 kilowatt EPS output on it. I've wired it directly into a socket down here, as you can see, and that's because I don't want any RCDs in the way when we come to do our testing. Typically you'd have that going into a changeover switch or a smaller distribution board for some emergency power supply circuits to run from. But in this case we've just got a single double socket, and I've plugged my TNS MFT Pro into it, and we can see we've got 245 volts ish between line and neutral and between line and earth, and 0 volts between neutral and earth. I've got it on no trip because there are some RCDs on the circuit feeding down to here, and even in island mode I will keep it on that no trip test just for some consistency in the instrument. Obviously we're disconnected at that stage from any of the input coming into the inverter. However, there could be some RCD technology built into these anyway that may start upsetting it, but it was more just for consistency in the testing. So if I hit a test, this is while we're connected to the grid. So we're currently running in combination with the grid. The battery's doing its thing, covering the loads of the building, but we are working off the main supply as earth and that grid input. And we can see we've got 0.5-ish ohms for our LPE loop and 0.62 on the line and neutral loop. Small difference there due to the bonds, gas, water, steel frame and such. You will get variation because of that. The supply in this building is a TNS. So that's why we're getting some subtle differences there. So that's in the grid connected state. Now to go into the island mode, if you like, we need to disconnect the AC feed coming into this inverter. And I can do that by this rotary isolator. It disconnects his line and neutral. So if we do that, you can see it's swung over on the display here. We've now got 232 volts between line and neutral and 232 volts between line and earth. And note the 0 volts between neutral and protective earth because this has a neutral earth bond relay built into it. You may have heard it click in as the grid dropped out, and that bonds the neutral and earth together inside the inverter. So we've got that in place. Now if I hit test again, so we're now in island mode. We're not using the grid side of things whatsoever. However, the earthing system is all as was, so it's all the same earthing components. We do have an electrode on this system. We have got a steel structured building that goes into the mass of earth, and we have got our TNCS suppliers earthing arrangement and bonds to gas and water. And you can see it's come up with 3.7 ohms on the LPE value and 3.66 on the line and neutral, so slightly higher on the line to protective earth. And we've got 47 amps of fault current. Now a point of note with this, if you reference into the battery storage EESS guide from the IET, there's reference to doing tests like this and how they have little value because of the way the instruments work alongside the inverters. There's stuff going on there at an electronic level which kind of makes these kind of numbers not the meaningful insight that we might think, but it's still interesting nonetheless, I think, to run that test and just see what it actually produced. And this is where the complexities come around the earthing systems as well. We know now when we're in an island state, the earthing system is TNS. That's because your inverter uses the earth as a reference for itself as a generating set within the installation while you are in island mode. I have a slight concern with that, where we maintain our connection to the DNS earthing system, because obviously out in the grid of things, while there may be a fault out there in that network, we are still connected into it. So I view it more as a hybrid. We're not fully detached. The DNS earthing system is still coming into our premises, and there's no fault out on the grid at the minute. I've just turned the rotary isolator off, and it's just serving two different purposes, I guess, but all at the same time. And it can cause a bit of confusion, and it is semantics, I guess, a lot of it. But yeah, I think that's something we need to bottom out as industry, because just referring to it as TNS, pretending that those other things aren't at play, you know, in theory isn't right, and I think that should be sorted out. But just a personal view there. So yeah, that was interesting. If we now restore power, so if I go back into here, you will see as soon as I do that, the inverter starts to check what's going on. And it's now made a grid connection back into things, but you can see it's dropped out the neutral earth bond relay, because it's not allowed to maintain that when the grid connection's been brought back in. And now it's sat there thinking away to itself about what's going on with the grid. It's got the wait time of sort of 20 to 30 seconds where it just decides that the grid has returned to a stable state, and it's not just a linesman or a jointer or whatever pushing connectors together and they maybe haven't quite finished their repair work. So it's allowing that wait period, and you'll have heard the clicking and clunking, and we've now gone back into that grid connected state, and we've now got the neutral and earth bonded together through that out in the wider install, rather than the inverter itself. So it is interesting to see how quickly it swings over into the EPS state when the grid is disconnected, and how it has that little wait time before it reconnects back to the grid on restoration of that, if you like. And I guess that's just for the safety side of things more than the technology's capabilities. Just to demonstrate that again, if I take the grid away, you can see it's quickly swung over into that EPS mode. The neutral earth bond relay is in place, and it's outputting 230 volts, for want of a better way of looking at it. And again, if we put the grid back on, it waits a little bit just to see that that is in a safe state. It has to take the neutral earth bond relay out because it can't have those in place when it does make that connection back to the grid. And then it's just running through, making sure the voltages are stable, the frequency's right, and it's a safe condition to re-energize the installation on that as well. It takes about 20 seconds or so. In the time I'm talking to you now, it should be coming back in. You heard that final click in the relays inside the inverter there. And we're now back at 245 volts. There's some great books out in industry. This is one that I really like. It's the Code of Practice for Electrical Energy Storage Systems. It takes you through some of the things that are and aren't allowed in the way we're setting these things up, and also some of the value or not within the test measurements that we can take out in the real world. And I just find this kind of thing interesting. As much as sometimes the data that is resulting from it maybe isn't as accurate as we might think, I know from working with the TIS MFT Pro Plus as much as I have, that it is a very robust and reliable instrument, even when you are very close up to TX transformers on the grid side of things, taking your ZE and ZS measurements, where instruments like this would usually be quite inaccurate due to that close proximity. This is one of the better ones in that application. Admittedly not as good as some of the ones that go to a greater decimal point that are specific for that task. Your multifunction testers are not designed for that purpose, have been less than a metre away from the TX when it's putting power out and you want to get a loop measurement. You know, there are specific instruments for that. But yeah, I think this is pretty interesting. I just find it interesting. Every proper experiment requires an assistant, that's me, and a maverick eccentric who thinks of things that we should do. You will note we've made some changes. I've taken feedback from Bruno in what we need to be doing. He's the brains behind all of this. He's also outside of the RAMs, and he has private medical healthcare. So we're able to push the boundaries a little bit beyond what we might be able to do if this was all my idea. So top work from Bruno. He's just down here. He is here supervising, just to prove the point. We've made a few changes, and it really is, having sat and edited the video in its rawest form, I thought there's a few bits we could cover off in a bit more detail if we just made some adaptations. So I've done that. You can see we've now got the EPS port running out over into these Proteus blocks. There is the singles on show here, but that's really so I can demonstrate what we're doing through the test process for you to be able to visually see it on the video. And we've got a little consumer unit down here with an RCD in it, and then a socket or two running off from that. So that's all on the EPS circuit. Now, there's voltage been measured down there. We're currently in grid connected state. All of the equipment is connected as was. So we're going to quickly run through those first tests where we do our ZS measurement both on grid and also off grid. I've also noted with editing the video that this test set didn't come into focus. It's too bright with the camera further away. So I'm going to bring you in closer, get off camera and run through this with you up front and personal, so to speak. So I'll get you off the tripod. Okay, so bringing you in, you can now see on the display we've got 245 volts. We are in grid connected mode, so there's no isolation of the power. You can see we've got that on into there. We're in no trip, we're on 30 milliamp. If I hit test, we should get a similar reading to the last time, maybe a little bit higher because we've now got a longer lead and some of the singles wiring inside this little temporary board that we've repurposed, and we should get a value. We're getting 0.86, so it's a little bit higher and a couple of 100 amps. And again, that's just through the singles cabling that's in here. We've got this longer cable feeding over from the EPS port. It all adds to that impedance path, but you know, roughly speaking, it's to be what we would expect. So if we go back to the voltage screen now, and you'll hear the clunk of the isolator. It's not a wide enough lens to show you and have that. I don't know if you can see that on camera. I'm working from a really small screen on the back of the camera. You'll just listen for the clunk. I'll go quiet and then you'll see how fast this switches over. So you can see we've gone into off-grid state now. We've got the 230 volts and we swung over quite quickly. So we can repeat the test. If we hold test down, again on no trip, because there is an RCD inside here, and we should get a measurement. And again, this should be very consistent with what we found last time. We'll speak a little bit about why later on in the video, but you can see we've got 40-ish amps and we've got an LPE of 4.25 ohms. And again, that's the wiring within this consumer unit leading it off to these final circuits. I think it is actually twin and earth on these, so the CPC is smaller rather than singles. Yeah, it's not conduited up, so we would have used twin and earth in there. So that explains the slight difference on that to what we was measuring before. So that gives us that side of things covered off. If we pop the power back on, we can run through this process and you can see the voltages. So it's dropped the neutral earth bond relay as it has to do because we're now connected to the grid into the inverter. We can't have our cake and eat it, where we're saying we can't have a neutral earth bond on a grid tied system. That inverter is now sat on the grid, although it's not outputting the voltage through the EPS port, so it floats for a short while. We have to have that wait period for the DNS side of things, the ESQR regs or whatever, where it's checking the grid's in a safe state. It takes roughly 20 seconds and then it makes that connection back to grid mode. So we're now grid tied again with the inverter. Now, Bruno, in his wisdom, thought, how about if we disconnect the earth when we're off grid and carry out that test again for loop impedance measurement and see if we still get a value. So I thought about disconnecting the earth out the earth block here. Bruno said that was far too safe, so we should disconnect the incoming earth from the inverter and see if this will actually run, and when it's off grid, carry out that test. So I'm going to quickly pop the camera down, isolate this safely, go inside there and disconnect the earth, and then under controlled conditions with my Maverick experimenter and his suitable private medical care, carry out that test. So I'll just pop this down and we'll jump back in a sec. So you can see inside here I've just popped the earth out, so we've still got the earth connection in there for the final circuit. Sorry, no, for the circuit coming in. So earth's still terminated at the back of this isolator. However, it's not connected going to the inverter. So it's essentially lost its earth now, it's just in and itself. Obviously the power's off, it has defaulted to island mode, so we can show you over here, we've got voltage on there. So we can carry out that test now and see what happens. So the inverter is still running off grid. It's created its own reference to earth. You can see it's holding 232 volts between itself, and it's still got the neutral earth bond relay in position. So if we hit test again, let's see what happens. Hopefully nothing sparks and arcs. That'd be a bonus, because I'm not convinced in Bruno's actual methodology here. But it's interesting all the same to see what values, if any, we get. And you can see they're almost identical. So we're still measuring a value for LPE and LN. And that's for the way the inverters actually work. When we're looking at the earthing side of things, really it's for our ADS with the bond of our earth coming in, if you like, to our transformer. That is giving us operation of our overcurrent protected devices. However, it's going to be interesting when we do some RCD testing in a minute to see if that will operate with the main earth disconnected, and if the inverter is able to do some magic in itself without an earth reference and still operate. That is going to be an interesting experiment. So we might as well do that in a second actually before we put the power back on. So just to explain again what we've done there, we've basically disconnected the main earth coming in. So this has now no earth connection anywhere other than the one it's creating in and of itself with that neutral earth bond relay, if you like, at its own transformer. It's hard to explain, it's easier to draw out and think about it yourself, and those values are pretty consistent, and it was happy to do that. So that's interesting. Is what I'm going to do as well. I think I'll have to speak to the brains behind all of this in a second, but we'll pop the earth back in, and then we'll just disconnect the earth on this outgoing side here from the consumer unit and see if it will still measure. So we'll do that after we've done the RCD test while we've got it like this, just to save putting it back together over and over. So yeah, just to explain that, we'll pop the earth back in, so the inverter essentially will have its earth connection, but we'll disconnect our earth coming to this consumer unit and we'll see if it will measure a loop impedance value. I'm going to say it won't, but we'll see when we get to that stage. So anyway, let's jump out and we'll do some RCD testing. 30 milliamp, we're on 1 times, let's change it to 5 times, just to make sure we've got plenty in there. So now we can see we've got voltage again. We've got no earth connected into the inverter other than the one it's creating in and of itself. So no earth electrode going in, no DNO earths going in, it's all separate. And we'll see if it will operate the RCD in here when we test it. So if we hit test, 7 milliseconds. So it's taken that RCD out, even with no earth connected in to itself outside of the one it's creating in the inverter. So that's an interesting experiment. I can't repeat that in grid mode because when it goes to grid mode, it basically connects the EPS through into the main side of things, and it would still trip the RCDs up front of this inverter, supplying it from the distribution boards, and we'd just have RCDs popping absolutely everywhere. So it wouldn't really serve any purpose. One would go before the other, but just to show you that in the off-grid state. So I think having spoken to Bruno and reviewed matters, we're going to pop the earth connection back in now while we're off-grid. So there's no voltages in this isolator at present, and then we can take the earth out of this earth block and repeat some of these tests and see what actually happens. So I'll just pop you down again so I can safely work on this. So I've now reconnected the earth back in here, popped the front cover on, but we are still in that island mode state. So I've not re-energized the inverter, we're still off-grid essentially, and I've disconnected the earth coming over from the inverter to this block, so there's now no earth running down into this consumer unit. And you can see on the voltages now starting to go a bit crazy, but we've got 232 volts between line and neutral, and it's kind of showing us 0 volts between line and protective earth, and also between neutral and protective earth, because the earth is essentially disconnected. So I'm expecting if I hit test, it's got a missing PE detection on the actual instrument. So that's showing us there is no earth connection in here and it won't run the test. So this kind of proves in and of itself that, like visually, that the methodology in the books and the way it's telling us that this is working as a TNS system plays out as true. But when we're disconnecting the earth from in here, we're not actually got an earth reference, if you like, so there's no earth electrode connected, If you imagine this is a generator out in a field or something, you've just kind of left it floating with no spike in the ground, it will still operate, it will still form that earth reference in and of itself for when you're running your tests and things. There's still that path back to the source transformer. However, it's not referenced to any actual mass of earth, if you like. But when we disconnect the earth out of here into this consumer unit, we are actually disconnecting earth, essentially, even if it is the one that's been created from the transformer. It's no longer in there, it's not showing in any of the test values. We can't do an RCD test. If we go into the loop impedance test, I'm expecting this won't run either, and it won't. So it's saying there's a missing earth. So just as an interesting experiment there, to kind of try and set out visually how this works. We'll have a look at the books as well and run through it in just a sec, but I'm going to reconnect all the earths, make all this back safe, re-energize things, and I will just maybe do a last test or two in that state, having checked with Bruno. He's a bit of a liar because he said he's got full private healthcare and he's just sat down there sleeping and not pressed any of the buttons. He's literally left me doing it, which is a bit of a liberty. So earth's back in, pop the power back on. We'll see it should start to float again as it's dropped neutral and protective earth. You can hear the relays clunking over inside the inverter. It's doing some checking now with the grid. Has to go through this process because we've got mains voltages into the inverter. Can't have a neutral and earth bond within it at the same time as that. So there is this little period, ESQR regs, where we need that little wait time before it will kick over. And you can see it's done that now. It's 10-20 seconds, something along those lines. And we're back connected. Now, if I was to run an RCD test, we might as well just do it and see what trips. All the lights will go off in here, I'm sure, as it takes the upfront RCD out. In this location, I'm very overconscious of safety because of what we do with learners and such. So there's lots of RCDs in series. As much as that's not very good for selectivity, it gives me peace of mind that at every stage along the way we've got something that can operate. But if we go back to the RCD test, we're on 5 times. Let's see which one happens to spring out first. So the lights have gone. That one has actually operated, so it's taken that one out. If we swoop over here, see how far back it went. This one, actually, it's this one up here. So that stayed on. So it must have taken the one out. Down here. Let's see. Yep, pop that on. Lights have come back on. So a couple of them went. That's a demonstration of selectivity with your RCDs as well. Interesting, isn't it? So if we go back, you can see it's had the grid voltage restored. Inverter's now doing its thing to resync back to the grid. We're going to have a look in this, dig this out. Bruno's hard at it, he's really working his brains down there, so he's going to point me in the right direction. We'll have a little chat about some of the theory side of all this, having demonstrated it practically. So my assistant did just think it'd be worthwhile doing a 1 times test on the RCD while off grid. So we'll do that. 25 milliseconds, that's interesting. So we can reset that now, get the voltage back present. And if we go to half times, and just to say this is with the earth disconnected in the rotary isolator again. So we'll see, it should hold this time. So interesting, it behaves as it should, even with no earth, in the way that we would normally speak about earth connected into the AC rotary isolator. But obviously this thing in of itself is doing what it does. Okay, so I thought we'd have a run through the code of practice. Held it in front of my face there because I'm not sure where I'm going to appear on screen, but this is for electrical energy storage systems. It's the 3rd edition. It's a really good book. You can buy it from over at the IET's website and other places of your choice. There's not a lot in here I'm going to dive into because we're not allowed to duplicate and copy loads of books. I'm led to believe in a discussion I had with Darren Cranis the other week that we can look at 10% of a book, but I do kind of have rough permission to share some of this because it is going out to trainees and apprentices. That's the core aim of a lot of the content I share. So it's not for copyright reasons, so don't beat on me. We are looking at section 9 here, which is the design of an EESS system. And we've got 9.4.4, which is general considerations. And basically it's telling us that we're allowed to keep the main earthing from our distributor connected when we are in island mode, but we can't rely upon it, basically. So we can see there's a regulation that's highlighted in blue there that emphasises that. And it says as consumers are not permitted to combine neutral and earth functions in conductors in installations that would normally be connected to the supply from the distribution network operator, DNO. The design decision for the majority of EESS operating at low voltage is whether the means of earthing in island mode should be TNS or TT. Existing TNCS and TNS installations might not have existing consumer earth electrodes. In this case, new electrodes will need to be installed along with the EESS, and it points you to a section of this book to look at that. TC installations will have existing consumer earth electrodes, but their suitability for earthing in island mode should be ascertained prior to installation of the EESS and upgraded where necessary. So if you've got an existing TT system, we did one of these actually for a customer of ours, Matt Telford, and he had a couple of earth electrodes on his system already that were more than suitable for what we were setting up, and we was able to utilise those without adding any extra electrodes for when and if he ever went off grid. TNS island mode arrangement. TNS generally provides a lower earth fault loop impedance than TT in island mode and is therefore preferred. The actual means of earthing arrangement selected depends on one or more of the following factors: the design of the system itself, whether it contains an isolating transformer and the neutral switching options available, the on-grid means of earthing and the availability of earth electrodes, and the energy available to operate your protective devices. So that's your short circuit currents. As you will have seen earlier on in this video, and we're doing the testing, the fault current that we've got there is quite low. We were clearing 40 amps, and that comes back to a point we'll look at later on in these pictures as well for the rule of thumb that you can apply in lots of cases if your inverter manufacturer won't provide you with that value. Operating as TNS in island mode ensures that loop impedance for earth faults are minimised, where the supply arrangements are TT. Operating as TNS in island mode offers improved protection against earth faults, and therefore this is recommended. Figure 9.5 provides a simplified illustration, so you can go and look at that. I'm not going to share it in this video. And then it just mentioned about IT. So we've kind of discussed that through the testing, that when we disconnected our earth in a roundabout way, that's kind of what we had. But it says, in dwellings, an IT earthing arrangement or electrical separation shall not be used for circuits operating in island mode. An IT system or one relying on electrical separation is rarely feasible for island mode operation for a variety of reasons, including the following. You've got your class 1 appliances. Hazardous touch voltages may result from noise filters, suppressors in class 1 equipment. Class 2 equipment with functional earthing, such as power supplies for electronic equipment. Many items of equipment in use in modern installations have interconnectivity options that may impart earth potential. For example, a computer connected to a device via a screened data cable that is connected at the other end of a PEL system would provide an earth connection. So all kinds of considerations around there. I'm going to close that page off and we'll open this one up. And this is talking about the neutral of the system. So we're going to skip by the rest of the chat around what we was just talking about for your earthing side of things and just look at the neutral earthing. So it says, in most situations, switching into island mode will mean that the grid connection between neutral and earth will be lost, and a new connection between neutral and earth, a system referencing point, needs to be provided for the duration of island mode. It's important to ensure that there is no more than one system referencing point in the system at any one time to comply with the ESQCR requirements. As we've mentioned in the course of this video, you can go off and look at what those are if you wanted, but also preventing any unwanted operation of RCDs. So if you've got consumer units in other parts of the dwelling, you may operate your RCDs if both of those things exist at the same time. And again, if you draw it out, that will make perfect sense. For a TNS system where the neutral is not isolated, any RCD shall be positioned to avoid incorrect operation due to the existence of any parallel neutral earth path. So it mentions it in there. It says where the DNS supply to an installation is provided by LV, disconnection of the supply neutral by the island mode isolator will be required to comply with BS 7671 and the ENA recommendations G98 and G99. So there are rules in G98 and G99 for what you can and can't do.
Consequently, in TN and TT systems, it's necessary to provide suitable switching arrangements to ensure that all live conductors, including the neutral of circuits to be powered in island mode, are disconnected from the neutral or pen of the DNO supply, and a single system referencing point exists in either island mode or on-grid mode of operation. A switch that provides a system referencing point during island mode operation should be interlocked and operate as described in 9.4.8. So a transfer between connected and island mode and vice versa is achieved by operating the switching devices. So as I was saying with the inverter, you can't have the two things in place at once, and that's where your hybrid inverters are a little bit different to if you've got, for example, a gatewayed system, because then your generators are held away from the gateway, so you can have your grid voltage come into the gateway, the generator sets can maintain their islanding state for longer, and then the gateways kind of check the grid voltages for that 10, 20 seconds, whatever it is, and brings it all back together. But when you've got a hybrid inverter and you're using that as your changeover switch essentially through the EPS circuit, it can't have that grid neutral earth bond and your islanding one together in and of itself at the same time, so you do end up with that little changeover. I'm not sure the industry of things really understands how that works with hybrid inverters. So there's some grey area in there between product standard and wiring standards, I guess. If we now look at section 12, and this is the earth fault loop impedance, which we've really been looking at through the course of this video, and it basically tells you in a roundabout way that you can't test it. So it's telling you when testing in island mode, a PV inverter may appear to act as a constant current source. It may indicate a far higher than usual prospective fault current before the current limiter kicks in on the equipment. I don't think that was the case here. I think it was measuring a genuine value, but it's open to interpretation. And to be fair, I tried the test with other test instruments. I'm not going to say which ones, and their readings were nothing like as consistent and I think as reliable as what the MFT Pro Plus delivered. I didn't include them in the video because I don't want to kind of discredit other brands' instruments, but I wasn't able to get them to behave correctly, or I would term as correctly. So I do think the values we were measuring were kind of accurate in and of what they were, but that's just my assumption, having worked with the TIS MFT Pro quite a bit. And there is a part 2 to this video that we've already recorded, which plays around with the harmonics and power factor capabilities of that test set. So we've done some other bits as well. So I do have confidence in that value. But it says here, when testing grid-connected inverters operating in connected mode, the inverter output tracks the change in the supply, so the contribution to protective volt current from the inverter is unlikely to be detected by the test equipment. So even when you are in the grid-connected state, it will have an impact. And it tells you here the following methods shall be used. And basically, you're kind of using calculation to do it. So you're measuring your R1 and R2s, inquiring for your ZE, and there is a little note here which says a rule of thumb for the current limit of an inverter is approximately 1.2 times the rated output of it. So this is a 6 kilowatt inverter, so if we do that 1.2 times on that, you're not a million miles out with the 40 amps ish it was measuring. So that rule of thumb is a good base point, I would say. BS 7671 requires that worst case conditions are considered for ADS and fault protection for prosumers electrical installations in dwellings, and these will normally be as followed. Connected mode ZE used for ADS is taken to be that relating to the DNO supply only. For thermal effects, consideration should be given to every combination of grid supply and local generation that could be operating. So, you've got your grid, but you've also got your inverters which are doing stuff as well. You need to factor all that in. Island mode ZE used for ADS is taken to be that relating to the largest ZE of any inverter configured as a grid forming inverter. So again, that's referencing the fact that you could have more than one inverter in your system. For thermal effects, consideration should be given to every combination of local generation that could be operating in island mode. And it's the thermal effects that are kind of the bigger, well, I'll say bigger, but the grey area to all this, and it comes back to your fault currents and if your overcurrent protected devices will operate if we are in a TNS system. And I guess that's why it makes sense really that RCDs would cover off both additional and fault protection, in my view anyway, to offer a better prospect of that. But yeah, that's that one. Determination of earth fault loop impedance. I think we've just read through that one, haven't we? Yes, so we don't need that one. It's just duplicated page. We've now got automatic disconnection in case of a fault. So this is from the wiring regulations. So we're going to look in here now just through what the actual regs tell us. And it says, except as provided by regulation 411.3.2, a protected device shall automatically interrupt supply to the line conductor of a circuit or equipment in the event of a fault of negligible impedance between the live conductor and exposed conductive parts. That's why you need, in the TNS system, the earth reference. And it says disconnection times required by regulations 411.3.2.2, .3 and .4. We'll have a look at that in a minute. And the protective device shall be suitable for isolation of at least the line conductor. There is a mention here of IT systems. Automatic disconnection is not necessarily required to occur within these installations. For the requirements for disconnection in the event of a second fault occurring on a different live conductor, see regulation 411.6.5. And again, for a medical environment, that's typically where you'll find an IT system. There are rules in and around that where faults can exist. So that's one to be aware of. Your maximum disconnection times stated in table 41.1 shall be applied for final circuits with currents not exceeding 63 amps with one or more socket outlets, and your 32 amps supplying only if disconnected current carrying equipment. I guess the grey area of this is a distribution circuit or not is for another kind of query, but that is of and what it is of itself. Let me see if I can find that table. So here's the table, and you can see for up to 230 volts, we've got our 0.4 seconds on TN and 0.2 foo's TT. So we've got those in there. There is the note around the 5 seconds here. In a TN system, a disconnection time not exceeding 5 seconds is permitted for a distribution circuit and for a circuit not covered in regulation 4.1.3.2. So these are these regulations that it was talking about on the other page, which kind of breaks it down a little bit further for you. But that's your time frames. If we have a look here, so this is just for regulations where we've got PCEs on, basically. So where automatic disconnection is not feasible in circumstances where electronic equipment with limited short circuit current is installed, or the required disconnection times cannot be achieved by a protective device, the provisions of regulations 419.2 and .3 are applicable. So for installations with PEC, I always get that wrong in terminology, but it's power electronic converters, with a nominal voltage greater than 50 volts AC or 120 volts DC, and where automatic disconnection is not feasible, the output voltage of the source shall be reduced to 50 volts AC or 120 volts DC, and that's kind of your touch fault limiting, or less in the event of a fault between live and earth, in a time as given in those regulations as appropriate. So it's kind of still telling you what you do need to do in the regulations, even if you can't satisfy ADS. So there is that mentioned, and there's a couple of other little pictures which I'm just going to open now, and they'll hopefully pop onto the screen. So it's this one for the RCD testing, and it basically tells you to test on the RCD, but I didn't want to open up live terminals, so we just did it from the local socket. But you can do your 2-lead test, so the upstream downstream method for RCD testing, and you've got your 3-lead test. And it says here, while the test method is used for 3-phase RCDs, the instrument test leads and probes must be rated for the line-to-line voltages, just to factor in there if you have got a three-phase system. And this example is included to illustrate the principles only. The person carrying out the test should take all practical steps to avoid risk of contact with large parts, and covers should only remove for the live test. In equipment where all line conductors have basic protection by their insulation or barriers or enclosures, achieving IP2X and IPXXB. So it's giving you a bit of direction there on that, just for your RCD testing. But I just wanted to mention that I just did it through the socket because it's a little test board, short length cable, but really you need to get onto those terminals when you are doing your RCD testing. Let's jump back to the rest of the video.
So I hope you've enjoyed having a look through how all of this has come together. We've dived into the regs a little bit to see the theory side and kind of how that maps out in the books, and then I've tried with my Maverick instructor Bruno to bring this to life and demonstrate how it actually behaves in the real world. And you can see through that experimentation process, I was just going to focus on the socket and just show a very brief overview of loop impedance testing, and then I kind of thought there's more we can do in the off-grid side of things with some RCDs. So I was fighting against having RCDs on because I know that up front of this there's loads of them, they would all just start operating. I just thought it'd be pointless. But then Bruno set me straight and pointed me in the right direction. So we've gone through that, and it kind of illustrates that, if we forget about the grid for a minute and the hybrid nature of earthing arrangements due to that, when we're off-grid here, this is TNS with that earth that we've got, so be that the structural steel, earth electrode, DNMOs, PME earthing system, the bonds, whatever it is, form that back to our transformer. It gives us that path on fault conditions, and if you draw it out, look at the diagrams, it makes perfect sense. But with that not in place, you kind of go to an IT earthing arrangement of sorts, and the overcurrent protective devices in terms of RCD operation do still work because it kind of forms that fault path back into and of itself. So you will still get that. I mean, the queries with all of this comes is if you've got enough fault current to operate your MCBs under fault conditions. If there isn't, is that a problem? So if you've got a, I don't know, 32 amp breaker and it's not quite generating enough fault current to operate, is your cabling going to be at danger because of that? All of this gets quite complex when you actually really start to look at it. And this is why the industry of things is kind of bashing it around still, I would say. We've got lots of guidance books that have come forward. There's other ones been rewritten around PV, battery storage, EV, on and all of this stuff. And that's because it is quite difficult to pin down. The technology moves so fast in what it can do and achieve. The manufacturers often will dictate certain things in the way their equipment can operate that's maybe different to the wiring standards, and it's that bashing together of product standards and wiring standards, and us as installers who have to kind of deal with that. But it was interesting to see as a demonstration, I hope you found it interesting watching, that even with the earth disconnected coming into the inverter, when it's just sat there floating in and of itself, that the RCDs will still operate when you do them on a 5 times and a 1 times test. So I found that interesting, if nothing else. I guess there's further experiments we could do in and of that, but this video's already got quite long, so we'll leave it there for now. And if you've got any questions, any input that you want to offer of other tests we can do in the future when we are off grid, things that you might want to see done under some safe working conditions with somebody with private medical healthcare, do drop them in below and I'll be sure to pass them on to Bruno. Otherwise, thank you for bearing with me through the course of this video. If you are somebody of industry and you've watched this, I know a few of you guys and girls do watch the content that goes onto YouTube from myself and others, and you've got a view on this, don't sit quietly on it. Don't send it over on DMs just to the creators. Get it out there in the public domain. Electricians are interested to hear your views. You don't need to be scared of having those opinions and sharing them publicly. I think that's how we all learn, develop and grow together. I think there's sometimes a fear that industry will be bashed down, and maybe that's what's happened over the last few years. So I totally understand that, where these communities have kind of built up and they've beaten on the IET, the JIB, the NIC, NAPIT, whoever, and there's kind of not wanting to engage at that level. So you just put your content out in your industry magazines and in your webinars and stuff, but the audience of all those things is shrinking and shrinking and shrinking, and if industry isn't careful, its mouthpiece to actual electricians at the coalface is going to diminish away, and all the content lots of people will consume does come from kind of YouTube and short content on social media. It's the nature of the beast, and if you're not careful, eventually the regulations will start getting delivered by those people in those ways, and it's maybe not been passed over to people in the way that you would want and the way that it should be understood. So yeah, without meaning to kind of try and lecture to industry, you know, I think that the days of fear in sharing your opinions and maybe being wrong now and again should well and truly be over. Just join in that discussion in the public domain where everyone can learn and develop together. That's kind of why I do these videos. I'm sure there's stuff in here that's not right, and some of the things that I've said and interpreted in a way that is wrong, and I don't fear that. I'm there to learn from people, feeding back, makes me better, and hopefully the people following along as well, watching and sharing and joining in the discussion. Otherwise, thank you very much for watching, and I'll see you on the next one.